Yeah, I would be, I is more of a symbol of a number because we don't know what that number is. We know what E is. We can figure out what E is. E, what happens here with the letter E, or excuse me, the number E, is that the number E is called the natural base E. And what I want you to look at this here, there is this old guy named Euler. He did a lot about math. I don't know. He's probably kind of smart. I think he hung out with Pythagoras. And what happens here is that this natural base E has been called Euler's number. And there's an approximation that has occurred as you look at specific things. What happens here is if you take 1 plus r over n to the n and you expand that towards infinity, it always is going to be approaching the same value, and that value is E. So let me show you how this works. Might as well give you a video instead of listening to me talk all the time.
Class, Paul McMatheny here.
I can only handle about a minute of this.
Great mathematician.
I kind of gave it away with my singing. Yes, it's me. We look a lot alike, right?
Found myself in times of trouble. Wise teacher comes to me, speaking words of wisdom, letter E.
Oh, God.
Oh, watch it. Don't cover your eyes. It's not that bad.
Oh, God.
He is standing right in front of me, speaking words of wisdom, letter E. Letter E. Letter E. Letter E. Letter E. Whisper words of wisdom, letter E.
I think it's just about enough to get it stuck in your head all day, and you're all going to hate me.
Logarithm, everyone would agree. There will be an answer, letter E.
All right. The cat.
Situation, it is natural for all to see. There will be an answer, letter E. 2.7 other 2.
There's your number E.
5904 523 628 7471 35266 249.
It goes on and on and on. Yeah, it's about enough. All you need. No. And this is crazy thing on computers called the internet. I don't know if you might have heard about it.
It's kind of weird.
It is a little bit weird. So again, what happens here is this thing is called natural base E. Think of it just as the number E. And what it represents as n approaches infinity with this basic idea here, as n is getting larger and larger and larger, the number that it is approaching, think of it as an asymptote that it's getting closer and closer to, is E. And they call E approximately 2.71828. It's kind of like the same idea of pi. It's irrational. It's a never-ending decimal. People still try to find the last digit. They're not as crazy as the people that look for pi. They're kind of like the...
But pie is more delicious.
I agree.
Funny.
So what happens here today is that we're going to talk about how we use E in terms of exponential growth or exponential decay. You'll find out that it's kind of like a shortcut for some of the formulas that we've used. Things like that. So the reason I put up on the board, on the whiteboard, exponent rules is that if we have E to, let's say, the third power times E to the second power, what does that become? E to the fifth. What's going to happen here is that we're going to treat this, oops, even though it has a numerical value, we still treat it with the same rules of exponents. You're going to see E a little bit more, excuse me, It's like you guys were asking, with some of the chemistry stuff. When you get a little bit further into it, you have to solve some weirder logarithmic style problems, some of the things, I guess. And you will have to use some of these properties. The properties we're talking about, again, if you have to play the game of war, where you're dividing out. If you have a negative exponent, you flip it. Things like that. So I kind of put up some quick reminders of what these things look like. So again, what we're talking about here today is we're going to kind of review some of the exponent rules with E. We're going to do a very brief how you would sketch graphics of this, how to tell if E is dealing with exponent, if it's dealing with growth or decay. And then I'm going to show you guys how you work it with some of the word problems that's similar to what you've done before. It's just a shortcut, believe it or not, from some of the formulas that we've already had. Okay? Hi. How are you? Good to see you. Come on in.
You have these two students.
Baby. Would you like that?
I just wanted to announce they got positive referrals. Tyler Schultz and Kirsten Bellin. Kirsten? Hello. All right, Kirsten, you got a positive referral for being hardworking. Unfortunately, the teacher chose to remain anonymous and did not sign it, so I don't know.
It wasn't me.
I don't know what teacher it was. And Tyler, you got one from Ms. Kavar for helping out in class. So good job.
Congratulations. See ya. What? See ya.
See you later.
So again, as you
Where's
go,
the monkey dance? There needs to be a monkey dance.
What?
Does anybody know what he's talking about? Then stop talking. Nobody knows what you're talking about. That means you shouldn't be talking. All right, take a couple seconds, see if we can simplify these out. Remember, all rules for your exponents apply the same way that they have in the past. If you treat E, even though it's a number, if you treat it like it was a variable when you're simplifying, it works the same way. Remember, you could have done that with digits as well. If it was 2 cubed times 2 to the 5th, it was 2 to the 8th. It works the same way. So take a few seconds, see if you can figure these out, and we'll check them.
Oh, yeah.
Things get to your head, you know? I have no idea if I was right. What's that?
I wanted to say with him there. What's that? He's looking some heads. He's trying to find E.
No, I'm just going down to
All right, what'd you get in A? E to the 7th?
Yes, sir.
All right, what'd you get in B?
2E.
Or not 2E?
Round of applause. That was good.
Hey, it's Monday. I'm all for it.
It's
Ready?
not Monday.
That is. In my brain, it is.
it's the start of the week, but tomorrow's Wednesday, and then the day after is Friday.
Great.
Tomorrow's actually
And there's like no flex at all this week, so rock out.
Wait, what?
Today's Wednesday, so there's no flex. Tomorrow there's a presentation during flex, and then Friday there's an assembly, so there's no flex.
Oh, okay, so what's the assembly, or what's the thing for tomorrow? Presentation?
KEC stuff. Available classes stuff. I'm going to talk about that here in a second.
Gotcha.
And then lastly, remember, when you have a whole bunch of junk raised to the exponent, you're basically distributing that exponent all the way across. So you have 3 squared and e to the negative 4x squared. So you have to distribute through. What do you do? Power to power, what do you do?
Well, you first gotta put the negative, you gotta put the e down one, because it's negative.
So it's 9. Now what is this? What is this over here then?
Yeah, it's a fraction.
Power to power, you multiply. So remember, this becomes e to the negative 8x, and that becomes 9 over e. Sorry, my hand's right sideways here.
Exactly.
What's 2 times negative 4? Power to power, you
The
mean?
X squared.
Power to power, you multiply. It's, yeah. The X doesn't, because this, when you have the exponent rule with this one, I think it stays. That's why I forgot that part. That was a weird one. No, it goes with it. It goes with it. Yeah. No. It's just 8x. It's the chunk itself. And that's like the only weird part. 'Cause you don't pull, yeah. Yeah, you just keep them together. Almost forgot that rule. So it just stays with itself as it drops down. Now, the other part of this, remember, exponent rules, take care of your numbers first and just watch your values. It's stuff you guys have all worked on. And the other part is, I'm not going to worry about calculators because you can type buttons. You know there's an E button on there? There's an E button.
There is an E button.
There is an E button.
Does it give you that long?
Oh, is it second LN?
I think so.
Reading?
What's that? They were working with, they were playing with stickers. Yes. Second natural log. That's the LN button. What's that?
No, it's the division.
Second divisor. Is that what it is?
Yeah.
Oh, there it is.
Oh, that one's either.
The other one's e to the x. That's right. That's when you raise it for graphing. All right, so this was
Oh,
pretty good.
I did 2.5.
So you can just put those things there. It'll spit it out for you. There's no reason to spend much more time on that. Yes, sir.
I still don't understand why that wasn't X squared.
What happens when you have x? When you have it with it, when it's e to the x, it just takes it as a junk, as the junk there. You just distribute it out that way. It's a little bit different from previous. It's that is the part. You just have to multiply it out by the 2.
So you only go.
It's just a weird set. Again, show you briefly of how these things work via graphing to show whether or not it's exponential growth or decay. When you're worrying about growth or decay, the graph that you're going to be looking at is this generic form of y equals a times e to the rx. That value of r is the one that's going to tell you if it's growth or decay. If the value of r is positive, it's growth. The value of r is negative, it's decay. That was tough, wasn't it? Okay. Again, when we graphed exponential growth, we graphed exponential decay last week when we had the AH and K there. It was much easier to plot points because you were able to find your intercepts and things like that a little bit easier. Here again, you're going to be able to find an intercept, but it's usually going to get one nice clean point. There isn't going to be that secondary easy point to find a lot of times with these things. So I don't spend a ton of time worried about graphing within E. Because when you're graphing with just the letter E, or excuse me, the number E, you're probably just going to be using your graphing calculator and getting your table set that way. There's really no reason for us to do the shifting with it, aside from just getting approximations. I'd much rather use this shifting with the exponential growth or exponential decay with AHs and Ks. It's a little bit cleaner than this, because these can get real nasty real fast. Let me show you what I'm talking about. Then it's still worrying about the exponent part. It's just remember how it could be first or fourth quadrant. It just depends on the direction of that. Graphic calculator will show you. We worry about the exponent here. In this case here, we have, if I'm going to graph this, 2e to the 0.75x. In this case here, is that going to be a growth or a decay? It's growth. All right. When I go to graph that, of course, my calculator still hasn't shown up. Come on. There we go. When I go to plot these things again, you're going to get one nice point, usually on it's your y-intercept, and then go from there.
Does that program cost money?
Which one? The emulator? Yeah.
You could probably find it.
You could probably find it for free. There's graphic calculator apps out there. There's a if you use Chrome, there's a really nice one on Chrome. Yeah, there's a real nice extension on that one that you can use. I forgot what it was called. I'll show you here in a second. What was it? Y equals 2. Now we want to go e to the x. That's when we use this one here. See how it jumps it right up to the exponent value? When the ln button, second ln. That ln is called natural log. I don't do it. Because I think originally it was called the log of the natural base. I made that up. And then you graph it. Again, you'll notice that you're going to get these singular curves. You'll be able to identify asymptotes probably rather easily here. What would be your horizontal asymptote here? 0. Now, when you go to plot points, just hit your table. And again, you should notice that you're going to find usually one really nice point, 0, 2, because that's your y-intercept. And then all your other points, because the value of e is irrational, it doesn't have a nice constant number to it. There's nothing that I can raise this to that would give me a clean integer spot. A lot of these things, there's a lot of fudging on your graphs as you're going to plot them. That's why I don't spend a lot of time graphing them. I spend time worrying about is it growth or is it a decay model and going from that. Does that make sense? So last little bit then is where does this get us as far as using in compound interest. Back in 8.1, we talked about compound interest when things were compounding quarterly, annually, things of that nature. We had the amount was equal to your initial principal times quantity 1 plus the rate as a decimal divided by the number of times it compounds, all of the number of times it compounded times time. Well, basically what happens here is that you can rewrite that. Oops, I just have it separated. As A equals P, the original principal amount, E, the RT. Pert. We're working with dandruff shampoo now.
Is there continuously compound decay?
That's what you were asking about earlier. I don't read things. All right. So again here, as we're talking about interest rates again, your value of P is your initial amount, your principal. Your R is your percent as a decimal. And then your T is your time again. What's nice is that instead of having to write out the big chunk in parentheses to solve some of these problems, you're using the button of E, and it just becomes a lot quicker. This is for your continuously compounding interest style problem. So if they say that you have, for example, if they say that you have, and I believe my next one has that, you deposit $1,000 into an account that pays 8% annual interest, compounded continuously. Continuously compounded. Continuously compounded means it's just always compounding. Continuously. Not quarterly, not semi-annually, it's just always compounding. It's money upon money. It's like you get a penny a day. Would you rather have a penny a day for 365 days, or would you have $100? Or compounding penny, 2 pennies, 3 pennies, and so on. I forgot how it works. Again, so we have.
Do you put 365 or do you put 1?
1.
But the next year, you make like another $3.
So again, start with 1,000. E. Push some buttons on the calculator, and you get your answer. Now, in the calculator again, this is where I'm going to use that e to the x button. So after a year, I'd have $1,083.29. And the reason we can use this is because it's continuously compounded. Okay? Instead of saying it's compounding quarterly, if it says continuously compounded, you use the per formula. It's compounding after a year. Does that make sense?
Okay, so continuously compounding is when you...
The only time you use only time you can use that is when it says it's continuously compounding. That's it for X amount of years or whatever.
And that's when it eats.
Yep. If it says it's what's that?
So the other ones were just like.
Yeah, you revert back to the other one because then that's suddenly it's compounding only 4 times instead of compounding continuously. Okay, it's once you see it when he says compounding continuous, it's perfect. If it says compounding quarterly, it's the other one, or semi-annually, or annually, one of those things. Daily, this works for daily because it's continuous. I'm saying this or that. It kind of works the same way through. Again, you wind up with some of the word problems where they're going to give you a growth model or a decay model in terms of E and excuse me. In this case here, that tells you that the species or whatever, the model was 119.6 e to the 0.0917 t. What would this be? A growth or decay? It's growth because the rate here is positive. The R value is positive. What is the rate? What's the percentage of this problem? 9.17%, good. So if they're asking you what the number of endangered species is in 1972, when this started in 1972, what is your T value? 0, it's time of 0, it's initial. So if what's anything to the 0 power then? 1, so how many species were there? 119.6 is basically what they're looking at. I don't know how you have 0.6 in the species, but whatever. Just like we did in exponential growth and exponential decay, if it says graph the problem, are you going to? Okay. Part C, use the graph to estimate when the species reaches 1,000. What are you going to use instead of the graph? Your table. Very good. So again, how do we check to see in their table what this is going to look like? Well, we go back to the graph, go to your y equals. It was 119.6 e to the 0.0917x. And I'm going to go to my table right away, and I'm looking to figure out how many years it takes to get to 1,000. Which one am I going to look for? X is 1,000 or Y is 1,000? Y. Very good. I just scroll through.
23, 24 years.
So you want to err on the side of caution and just say 24 years?
Why is it why?
Because you're looking to see what this is asking for you is when it reaches, the number of species is going to reach 1,000. So when you want this equal to 1,000, you're trying to solve for this. The value of t is basically your x. The 1,000 becomes the y, is what you're looking for. So instead of looking at it at a graph, it's a lot easier with the graphing calculator. It's just to scroll through and find out where it goes to 1,000, and I must have skipped it. It jumped to 1,000 between 23 and 24 years, so I would just err on the side of caution and say 24. Unless you're leaf in, say, June. Get that, it's halfway between the 2 years. June.
I thought you were talking about the person.
I was, you said that about one of the questions we had, like estimate what year. So you said the year, it said June of that year. Like, can't argue with that logic. So, questions? Fairly straightforward. What we're going to do this week is we're going to do this for today, and I'm going to try and make it more difficult on you tomorrow. Let me give you a couple problems to look at for tonight. On Friday, we will have a brief quiz over the first 3 sections. It shouldn't be that bad. This is 8.3, 483.
Except it's kind of hard. Let it warm up. Cold up. I walk back inside. Well, Monday, I just had people.
Try those. Those will be all. Don't freak. These are growth or decay. It'll take you 6 seconds to do all of those. Yes, sir.
Are we going to be graphing?
Not today. I'm not worried about any graphing today. The first chunk is simplifying the expressions using your exponent rules. The second chunk, is it growth, is it decay? The last chunk are a couple word problems. Yes, sir.
You know we haven't had a full week of school since before winter break, and we won't for another like.
We have a full week next week.
But
Other than that, we had another.
I know.
We've had 1 week and like.
I know. It's been a. This is the weirdest year I think I can ever remember with the way the weather and all that goes.
Yeah,